The top is stable.
Hey. Sorry. All right. So in this diagram, we have a protein. It's got two pretty stable states. We've got one here and one here. Does everybody see it?
Yes.
Okay, cool. So if this thing is in this stable state, we would need to raise the end temperature of it in order to get here.
Yes.
Everybody cool with that?
Yes.
And as we raise the temperature, the shape of this thing would change. Everybody cool with that?
Yes.
So it turns out that enzymes have these small ranges of activity. A time or a temperature range at which they're shaped really properly. Above that temperature, and I might be flopping around. Below that temperature, the enzyme can actually just not move very quickly.
Will it still move?
Could. Yes.
Can I come up there?
Please come on up. Wait, no, you can't be on camera.
Oh, I can't.
No.
Because
because
Privacy.
the waiver rules.
I'll have to wait until it's
What?
Well, put this
Why? But you
That's
uploaded
gonna
a
be
video
so
with Dylan.
I got permission.
Go, please go. It doesn't matter. I allow it.
No, you can't. Just ask a question.
Okay, well, there's like 2 points, or there's more. There's like a few points on that graph where it's in activity range. Will it like be active even if it's like going down, like on the second one? Kind of like no, more to the right.
Here?
Yeah, like it's still in the activity range, but will it be like serving?
So no, the activity range is specific to this shape.
Oh, so each shape has like its own activity range.
That's a very good way of putting it. Each shape will have its own activity range. All right. So another way maybe I could draw it is if this is temp and this is stable, right? So then another way I could draw it is saying like this activity range.
Oh. Yeah. Okay.
Right?
Yeah.
So let's say this is at 37 degrees centigrade.
Yeah.
So at 37 degrees centigrade, this enzyme works really well, which is probably the case for lipase. Lipase probably works best at 37 degrees centigrade.
Wait, can you redefine activity?
So sure, lipase, in the case of lipase, activity is going to be the amount of fat that the enzyme is breaking apart.
No, but like in your thing there, like
Okay.
what is the activity range?
So this is a shape.
Mm-hmm.
An enzyme is going to be in a shape here.
Okay. Mm-hmm.
That shape is going to be optimal for breaking down enzyme or for breaking down lipids.
Mm-hmm.
With me?
Mm-hmm.
Tom? Tom?
Hi, Luke. How's it going?
All right. As we move out of that range, we change the shape of the enzyme. As we change the shape of the enzyme, we change the function of the enzyme. Who's with me? Tom's. Okay. This is going to be really, really important for us. So, the thing to take away from this, and you can write this exactly down when you watch this video, is that enzymes have these like ideal conditions. And they're not just based on temperatures, but also on pHs and salt concentrations. Anything that's going to change the conformation of the enzyme. So if I put a bunch of positives in the environment of an enzyme, I'm probably going to mess up the way it's folding. Enzymes have very, very specific conditions. They have a specific temperature, they have a specific pH, and they have a specific ion concentration, salt concentration, at which they will work best. With me?
Mm-hmm.
Leona?
Yes.
Leona?
Yes.
All right. Yeah. Yeah.
So like with when you're like changing temperature and it's like going along, it's like it's roller coaster, right?
Yeah.
Is the ion concentration changing as well, or just the shape of the temperature?
No, but I can do the same thing with ion concentration.
Yeah.
So, right? So let's say this red piece is held together to this blue piece because the red is positively charged and the blue is negatively charged, right? If I what did I say? Red was positive?
Yeah.
So if I suddenly introduce a whole bunch of negatives, they might surround this negative, or this piece, and then this thing would lose its shape.
Yeah.
If I lose the shape of the enzyme or change the shape of the enzyme, I decrease its activity. It's always going to come back to charges and shape. Yes?
How does pH affect? I mean, pH is the concentration of hydrogen ions.
This is negatively charged?
Yeah.
If I put a whole bunch of hydrogen ions in here,
It's not going to hang out with them.
if they're going to surround this, this is not going to attract to this.
Right. Cool.
Cool? All right. Okay. One more?
That's an example of how charge determines shape. What about shape? Like, how does that matter?
What is shape?
Well, shape. So you just like dumped a bunch of pluses or a bunch of minuses. So that's all charge affecting the way that shape changes. Are there any examples of how shape affects how charges?
No,
I'm not
it's
sure.
the other way around. It's always the other way around.
Okay.
The charge will always affect the shape, not the other way around. I see what you're saying.
Not the best way.
Okay. The enzyme we're going to be dealing with is called Thermus aquaticus, TAC. Its optimal range, and we're going to have to check it, is going to be somewhere around 70 degrees centigrade. That's hot. Okay? So your body temperature is 37 degrees centigrade?
So that's like a solid like 200 degrees.
It's like 70.
I don't know what it is in the F
Wait.
word.
No, it's
It's
Okay.
70.
70 Celsius is really hot.
So don't forget we found this enzyme in an organism that lives in hot springs, Thermus aquaticus. So it makes sense that its enzymes are adapted for hot temperatures.
That's what's a house
Wait,
lab
I
with
thought
temperature
that
again?
DNA started to like unravel.
DNA will start to unravel at about
That's
that
about
temperature, but not completely. DNA actually, in order to get DNA to fully unravel, I'm going to have to get up around 90 degrees centigrade.
Huh.
I'm going to ask you to stop all questions, and we're going to actually start this over.